35, revolution and parallel scheduling. Many activities may be going on at the same time by many processors or agents, so each processor may be doing something while the other are busy. There must be a protocol establishing for access to resources or services, or there must be one processor which is in charge to supervise the coordination of the processors. Since there are many decision-making processors or agents and not one, and each one may have a different set of beliefs. So, now that was one. Also, the operating system, of course, was very interesting. You usually take computer architecture first, assembler, data structures, program language, and all this first, besides mathematics. But we also had a chance to write a parallel computers programs to parallel, like a supercomputer, parallel several processors. You had to synchronize them. Well, but there is, but one professor from later, one professor from Concordia went to McGill and he became the director of computer science. I took a graduate course. He let me take it at McGill, the computer science artificial intelligence graduate course. It's one of the top levels of courses at McGill. But anyway, then after I left because it was mostly um, just I wanted to do a computer expert system, but it was mostly just exercises, and I was tired of exercise. I wanted to get a real job already. And I didn't. I wanted to was running out of money, so I wanted to leave so I could work on some stuff that I was working on instead of doing these exercises. Didn't seem worth it. I had my degree already. Okay, revolution abstract thinking. This is number 36. Revolution abstract thinking. Unknown. Using a higher level reasoning language and later using a program to automatically translate it to a simpler level for the other people or machines to understand, e.g. like a compiler or interpreter. Compiler translates it and wants the whole thing. Interpreter translates it line by line while it's working. For example, writing in Fortran programming language for computers and having it translated by a Fortran compiler to assembler language or reading machine code. This can be very important since it has been found that programmers write about 5 to 6 lines of debug programs each day, no matter what language they use. By each higher level language is really several lower level lines of code. It's also easy to understand. So it's like, well, Fortran is like I think considered to be a third level generation language, like C and Java. So it's like 5 to 10 instructions are translated to one machine code. Now I have fourth generation languages like natural um, and others that are more like 30 to 50 languages translated to one language. There's a few other ones. There's hundreds of fourth generation languages now, at least for years, if not more. But so they're more powerful. So if you can write 5 to 6 lines of code, obviously it's better to use a fourth generation language than a third generation because you multiply it by 30 to 50 instead of multiplying it by 5 to 10 instructions. And it's easier to understand. So really writing a computer program now should be easier. Because once I know how to write a computer program in assembler, which is like machine code, which is a ratio of 1 to 1. I wrote in Fortran, C language, and all of that. Now if you have to write in fourth generation language, probably it's easier because each one is more instructions. That's one of the reasons why they want it, because it's easier to understand and easier to write programs. There's also the idea of reuse, because you don't want to write programs over and over again. You create apps or sub-programs, procedures, and you can use them over and over again. 37. Revolution in conventional artificial intelligence. The calculator has proven itself useful to scientists and businessmen, but one can also use high-level programming languages to create software that acts in intelligent ways. This can help us solve problems that we can't solve on our own. Using von Neumann's idea of a program stored in memory, it is possible to give a computer 1,000 instructions without having to intervene even once as it is working. Unknown, maybe John von Neumann. Okay, number 38, revolution in logical artificial intelligence. Okay, Aristotle, Immanuel Kant, Gottlieb Frege, etc. See also Niels J. Nielsen's book on artificial intelligence. I don't think there is as yet a standard masterpiece of artificial intelligence. In fact, they said they need a full-time Einstein artificial intelligence still. There's so much work to be done. But Niels J. Nielsen's book is really good. Okay. And then you have many contributors. Revolution in logical artificial intelligence. Another way to use the computer to help us reason. There are AI languages and language tools that allow one to simply enter the data. There is no need to enter the program or set of instructions to tell the computer what to do. That's the main difference between a conventional program and artificial intelligence program for a computer. In artificial intelligence, you don't have to enter the instructions or methods. You just ask a question or get the data mostly. The computer has it. In the conventional programming, you have to give, the programmer has to give the program, the instructions and the data. Although the computer itself has instructions in basic ones inside the central processing unit. So they're very primitive. Today's computers are very primitive. They only have the super method of arithmetic and the super method of Boolean logic. But here we list hundreds of reasoning methods. So you have to, in a conventional program, you have to supply all the reasoning yourself. So that's when people want to build an artificial intelligence machine, where you don't have to supply all these instructions. Well, sometimes that's why you buy software packages, because they come with all kinds of methods, but it does things for you. You have a menu, and you select what you want to do, and the computer will do it for you. The computer can do anything. Okay. Another way to use a computer is to help us reason. There are artificial intelligence languages and language tools that allow one to simply enter the data. There is no need to enter the program or set of instructions to tell the computer what to do, and the program will work. The program is already included which manipulates the data. It applies inference rules to the data to answer the questions, or it can generate plans to achieve a certain goal. This is only the beginning of what it can do. The program is also defined implicitly, unlike regular programs, which are more explicit or instruction-driven. It is more data-driven. There are many instructions, and the data determines which ones and in what sequence they will be applied. The order of instructions is not specified. There are several impressive computer expert systems using artificial intelligence today. For example, even in medicine. You have internist and which is for internal medicine, and you have myocin. This was a long decades ago, but kept improving. The way of medicine now is unless an artificial intelligence expert system is suitable, because they don't rely on methods as much now. It's mostly data. Okay. just have to check to see if a test result is within range. So that's all. So I don't think you need an artificial intelligence system. Artificial intelligence systems are not suitable for everything. But one day medicine may become like that. There are even symbolic artificial intelligence programs to do very advanced mathematics, like Mathematica or Maple. But there are still many methods of reasoning which must be added besides the version of modus ponens that is used today, which is just a variation of Aristotle's syllogism with multiple quantification of Frege added. Number 39. Revolution term logic. Gottlieb Frege, Jensen, Smulian, etc. Propositional calculus. This is a formal language for doing logic which is accompanied with a set of rules. Reasoning may occur using Jensen's natural deduction or Smulian's tree method, for example. It does not allow variables and hence no quantifiers. So the latter don't apply to variables, but they don't apply to predicates either. Frege may also have discussed this. Number 40, revolution in variable logic. Gottlieb Frege, Jensen, etc. The predicate calculus. This is a bit more complicated than the propositional calculus, but still limited. Multivariable logic. This is also a formal language for doing logic, which is accompanied with sets of rules. But first of all, the predicate logic permits variables and even quantification of the variables. You can even have multiple quantification. Aristotle had quantification, but only one of them. So I don't know, maybe he didn't allow for reciprocal relations. That might have messed up Kant's system. Because the series of causes can only go one direction. There's no feedback. Okay, one can have one can have single, double, or triple, even higher levels of quantification of the variables. But only in higher degrees of the predicate calculus it is permissible to replace variables with statements or quantified predicates as well as variables. In other words, this is the predicate calculus, but this is the basic. There are higher levels of predicate calculus which allow more, and this is a bit more tricky. But only in higher degrees of the predicate calculus is it permissible to replace variables with statements or quantified predicates as well as variables. Predicates really describe variables. Reasoning can be like Jensen's natural deduction. Frege seems to be credited with introducing the notion of multiple quantification. Since Aristotle, even up to the time of Kant, it seems that only single quantification was used. This is a big step forward, since it may be necessary to use multiple quantifications to say such things as Joseph and Lily love each other. In physics also, the electron and proton may be held together by reciprocal force. This oversight may have damaged Maimonides and Kant's system, since for the former the necessary existence according to essence could not be composite, and for the latter the series of conditions in our mind may flow in both directions, not just from the unconditioned to our mind, but from our mind to the unconditioned as well. Okay, that's page 18. Number 41, revolution of modal logic. Aristotle, etc. This involves reasoning which has propositions of different modalities. It includes necessary propositions and possible propositions, not simply true or false propositions. When something is necessary, then it is true in all possible worlds, not just this one. Or if it has a condition, then it is true in all worlds in which that condition is satisfied. We introduce a method of a priori reasoning that claims that some statements are true in all possible worlds, hence that the one thinking about them exists, and hence at least his world exists. So those a priori propositions apply to his world as well. This is counter to Kant's belief that existence is not a real predicate, or that existence cannot be given a priori. This is a very powerful idea. It's against Kant, but you can prove the existence of things because there are some things that exist in all universes, and our universe exists because we exist. So it must exist in this world also, so you can prove it a priori. And in some place I even merge this together with Einstein's theory of general relativity. So it's just an a priori and a